Anomaly detection is a critical process for identifying rare items, events, or observations that significantly deviate from normal data behavior. This area of study is crucial for maintaining the seamless and efficient operation of assembly lines. While numerous methods exist for detecting or predicting anomalies, the analysis and understanding of these rare events are less frequently explored. At the Future Factories cell within the NEXT laboratories at the University of South Carolina, researchers have developed an experimental testbed for a rocket assembly prototype system. This assembly line features 4 robots programmed to construct a rocket by assembling 4 key components: the tail, the nose, and 2 body parts in between. This video shows the expected behavior of the assembly system where the rocket is assembled and collected at the end. Now, what happens when an anomaly occurs? If a body part is missing, can we analyze the anomaly in addition to detecting it? An anomaly detection dashboard that is built to monitor the assembly system in real time will collect and analyze sensor values to detect anomalies. We can see that the robot puts with missing rocket parts into the conveyor belt to start the assembly process. Simultaneously, the dashboard shown below starts collecting the sensor data from the assembly line in real time to monitor the assembly process. The next robot picks the first part but fails to notice that one of the assigned parts is missing, but proceeds to operate anyway. A similar situation happens with the next robot as well. The robot puts back what it thinks is an assembled rocket back to the conveyor belt. Parallelly, the dashboard keeps collecting the sensor data to analyze if there is an anomaly. The anomaly detection model running in the background has detected the anomaly as top body and nose cone missing, which is displayed in the dashboard. Now, what if we need to know more about the anomalies, such as which robot is responsible for the anomaly detected by the model? Which sensor is responsible for it? What is the value of the sensor when an anomaly happens? Answers to such questions can shed light on the anomaly, aiding us in planning the next steps. In order to aid the domain experts in answering these questions, the researchers at AI Institute have developed a dynamic process ontology for the rocket assembly process to gain a deeper understanding by answering these questions. Unlike conventional ontologies, process ontology captures the procedural nature of the assembly process. The ontology is structured around 21 cycle states of the assembly line, starting from 1, 2, 3, and so on till 21. Each cycle state encompasses the respective robots and the specific functions they perform within that state. To add, the expected normal or anomalous range of the sensors within that cycle state is also captured, along with other information about the sensors. For each state, potential anomalies are also captured. In addition to the generic functions of robots, the ontology captures specific functions of the robot at a given time in the assembly process. The dynamic nature of the ontology lets us update the properties of the entities if there is a change in the experimental setup. For example, the expected minimum and maximum of the sensors can be changed if the equipment is calibrated for different assembly runs. Using the dynamic process ontology, one can gain a deeper understanding of the anomaly using the explanations provided by the ontology. For brevity and usage, only the robots along with their function during which the anomaly happened are listed here. The ontology can provide the sensors, their functions, and expected values along with it, which can let the engineers plan the next steps to overcome anomalies. Using the proposed dynamic process ontology, explanations can be generated for anomalies detected. It can be noticed that the ontology sheds light on this anomaly by answering which sensors and robots are responsible for the anomaly detected by the model, and what were the functions of these robots in each cycle state. These additional insights will aid the domain experts in planning the next steps.